Good morning. Hope you all are doing well. Today we'll discuss about the remaining expressions of concentrations. First of all, we discuss about the volume percentage, or it can be sometimes represented as V by V, or sometimes it is known as V by V percentage. That means volume by volume percentage. Okay. This is actually the measure of concentration of the solutes which are present in that solution in terms of volume. That means how much volume of that component or that solute is present in the total volume of that solution. This can be calculated, or this can be known from these expressions of concentrations, which is volume percentage of component. And mathematically this can be defined as volume percentage of a component is equal to volume of the components or volume of the solutes, okay, which actually we want to know how much of them is present in that solution, divided by the total volume of the solutions, okay, solutions. And we have to multiply by 100 because we actually are representing the whole expression in terms of percentage. So we have to actually multiply these things with 100. Understand? So let us understand this actually expressions by using some examples. Okay, let's suppose you want to prepare 100 ml 10% or 10 volume by volume percent ethanol solution. Okay, so for that actually our final volume should be 100 ml. Okay, and the concentration should be what? 10%. That means 10 volume percent. Okay, so that means since we are talking about volume percent, so that means we have to measure the the amount of the solutes or amount of the components. Here the amount of component is what is the component here, or what is the solute? Solute is your ethanol. Okay, because ethanol is in less than that solvent, which is water. Okay, so because we are talking about the volume percentage, so we have to take the ethanol in ml. Okay, that means 10 ml. We have to take 10 ml of ethanol and add water to make the solution 100 ml. That means actually practically we use volumetric flux, okay, to prepare this type of solutions. Actually we first add the 10 ml of ethanol here, okay, then we add water up to that limit. That means if the volumetric flux is 100 ml, then the marks, actually this marks represents that if we add water up to this limit, then the actually the solution inside that volumetric flux is of actually 100 ml. Okay, so why actually we use volumetric flux to prepare? We can also use just 10 ml of ethanol, then 90 ml of water. Okay, actually we do this type of or we use this volumetric flux to prepare volume percent solution to minimize the error. Okay, actually what happened, let's suppose we can also prepare this that solution, volume percent solution, by using just a beaker also. Okay, no problem, but error will be there. Error actually will come by mainly two ways. One is the human error, and other is actually the instrumental error. Okay, so in case of human error, actually let's suppose we are preparing that solution. Okay, so first we prepare, or first we just take a beaker. Okay, and in that beaker we take 10 ml of ethanol, let's suppose. Okay, and when we are trying to add 90 ml of water by measuring that water in a measuring cylinder, then when we are trying to transfer that water, 90 ml of water, from that measuring cylinder to that beaker in which actually the ethanol is present, then when we are transferring this water from that measuring cylinder, then what will going to happen? Actually unknowingly, actually some amount of water will remain inside that measuring cylinder. So we cannot transfer 100% of them from that measuring cylinder to that beaker. Okay, so that means some error will be there. Okay, so it will be not exactly 10 volume percent of that solution. Okay, and from this we are able to know that the human errors are mainly coming from our mistakes. Okay, and the second is actually your instrumental error. Actually instrumental errors are coming from the errors of the instruments, and in this case maybe from the that measuring cylinder. Maybe the scale of that measuring cylinder may not correct. Okay, so it will come from the instrument primarily. Okay, so we can minimize these errors by using volumetric flux. Okay, so actually each and every volumetric flux there are some marks. Okay, one ring is there like this. Okay, so let's suppose this is your 100 ml volumetric flux, and this ring, actually this mark is actually represents that if you fill some solution or some solvent up to this mark, then this mark will indicate the volume of that solvent inside that volumetric flux. Okay, so if it is 100 ml of volumetric flux, then this mark will indicate that the solution inside that volumetric flux, if the solution is up to this mark, then it is your 100 ml solution. Okay, and let's suppose this is your 250 ml of volumetric flux. Okay, and if you fill the solution up to this mark, okay, then the volume of the solution inside that flux will be 250 ml. Understand? So this is very simple. So by using this volumetric flux, we can actually minimize the errors. Okay, so in case of this volumetric flux techniques to prepare this volume percent solution, let's suppose we have to prepare 100 ml of 10% ethanol solution. Okay, so for that, what we have to do, we have to first take 100 ml volumetric flux. Okay, 100 ml volumetric flux, then we have to add 10 ml of that ethanol inside that volumetric flux. Then we have to add water up to the limit or up to that ring which is actually present in that volumetric flux. Okay, to prepare that 100 ml 10% of solutions or 10% that volume percent solution. Understand? Very simple. Actually this expression of concentration, that means this volume by volume percentage or volume percentage of solution is used to represent liquid solution. Actually, if the solute is also liquid and the solvent is also liquid, then we can use this expression techniques or this expressions, this way of expression of the concentrations. Okay, and for example, you can take that ethylene glycol. Actually here in the book, actually it is given that 35% volume by volume solution of ethylene glycol. So this is actually used as a antifreeze solution or antifreeze tube, which is used in actually the car engine. Okay, actually in some places like some hilly areas or some areas where the temperature of the weather is very, very low. Okay, so in such cases, actually the water can freeze because it is below 0 degree in some places. Okay, so the water can freeze. Then if the water will freeze, then the water cannot circulate that engine to cool down that engine. Okay, so for that, actually it will be used, that means the ethylene glycol, which is actually used as a antifreeze, which will actually decrease the freezing point of the water to actually minus 17.6 degree. Okay, so it will not go, the water, if we add the ethylene glycol in water, then it will going to decrease the freezing point from 0 degree to minus 17.6 degrees Celsius for water. Okay, so this is a very good example. So that means here you see, here the concentration of this that solution of that ethylene glycol is represented as 35% volume by volume. That means here the solute, which is ethylene glycol, is in liquid form and the solvent water is also in liquid form. That's why we can use this way of expression to represent the concentration of these solutions. Understand? And the last way of expression in which we use the percentage, okay, is actually mass by volume percentage, which is represented as W by V also. Okay, sometimes it is represent W by V percentage. Okay, so in this case, actually this representation is used mainly pharmaceutical industry or medicinal industry. Okay, because by using this expression, we can determine how much of some components or some medicinal value components will be present inside some particular solution. Okay, so it is represented by W by V. That means with how much weight is present inside that solution. Okay, mainly it is represented by that amount of that solute or that component in gram or sometimes milligram in 100 ml of solutions. Okay, so these three are mainly about the percentage of actually we can use the these three techniques to represent the concentrations in terms of percentage. So how many percentage of solutes are present inside that solvent, we can represent this by using these three way of expressions. Okay, so now let us discuss about the fourth way of expressing that concentrations, which is known as parts per million. So this is a very important actually way of expression of concentrations. If the the concentration of the solution is very low, okay, then we can use this parts per millions way of expressions of the concentration. Okay, so let's discuss about this parts per millions in details. In the previous cases where actually we use that 100% or percentage, in those cases actually we are trying to find out the amount of solutes which are present in 100 ml of solution or 100 ml 100 gram of solution. Okay, that means we are just trying to find out the solutes which are present inside that solution in terms of percentage. Okay, let's suppose as for example, let's suppose suppose X ml of solution has Y ml of that solutes, then in 100 ml of solution Y by X into 100 percentage of that solutes is present. Okay, so it is actually we are trying to find out the amount of solutes which are present in percentage. Okay, but in this case actually we will actually try to find out the concentrations in 10 to the power 6 terms. That means in millions parts, how many parts of that components are present in million of that solution. Okay, in terms of that million parts per millions. That means let's suppose it is let's suppose X ml of that solution contains Y ml of that solute. Okay, then in 10 to the power 6 ml of that solution contains how much of that solutes, we will try to find out like this. Okay, that means we are here in case of parts per million, we are trying to find out the amount of solutes, okay, which are present in that solutions in terms of parts per million. That means how many parts of that solutes are present in millions. Understand? We use this this way of expressions in case of mainly in very dilute solutions, because why, you see, in case of dilute solution the solutes which are present in that very dilute solution will be very less. Okay, that means it is very difficult for us to represent the amount of solutes which are present in that solution, because this is very less, very minute amount of solutes are present. Okay, so if you increase the amount of the solutions, then also the solute amount is also going to increase. Okay, that's why we increase the amount of solution into millions. That means 10 to the power 6 terms. Okay, then the amount of solute will also going to be a considerable amount. That means we can have a significant amount of solute in a very huge amount of solutions. That means in 10 to the power 6 terms of solutions. Okay, and mathematically this parts per millions, also this is known as ppm. Okay, ppm can be expressed as, actually ppm is equal to number of parts of that components which is present in how much, actually 10 to the power 6. Okay, and this 10 to the power 6 means what, a million. Okay, divided by total number of parts of all components of the solutions. What is the meaning of all components? All components means it includes the solutes and that solvents also. Okay, that means mainly the solution, it's talking about the solutions. If you actually we can express the this number of parts of the component in terms of mass or in terms of volume also. Okay, if you it's like the previous cases. Okay, so here it is given actually in your book, the as in the case of percentage, concentration in parts per million can also be expressed as mass to mass. That means we can use the number of parts of that component in mass and also the total number of parts of all components, that means the solution, okay, the total, that means the solution solvents in mass also, how much solution solvent are present, okay. So that means we can use in the number of parts of components, mass of that component divided by what, mass of solute plus mass of solvent, like that, okay. And also we can express them in terms of also where by using volume to volume, that means volume of the components divided by volume of solutes plus volume of solvent. Here component means solutes, okay, and solvents both. That means here again we can also use the mass to volume also, okay. So this is very good because we can express them in any one of them, okay. So here also one example is given, okay. So let us discuss about these examples, okay, because in these examples, if you look at these examples carefully, then here you see the concentration of that solute. Here the solute is oxygen, okay. So concentration of the solute is very less in comparison to the that solvent, okay. So let us discuss in details about these examples. So if you look at this example, here you see total 6 into 10 to the minus 3 gram of oxygens are present in 1030 gram of water. That means a very little amount of, a very minute amount of oxygens are dissolved in actually almost 1 liter or 103 gram of water, okay. So it is a very less amount of solutes are present. So we can express the concentration of these oxygens which are present inside that water in terms of ppm or parts per millions, okay. So for that, what we have to do, we have to first divide the amount, actually the amount of this oxygen as well as the water is in gram, that means mass by mass, okay. So we can use that mass to mass, the first way, okay. So here what we have to do, we have to divide this 6 into 10 to the minus 3 gram by the total number of or the total mass of that water plus the solutes, okay. That means by 103 gram plus 6 into 10 to the minus 3 gram. So this 6 into 10 to the minus 3 gram is coming from that solute, and this 1030 gram is coming from that solvent, okay. And we have to multiply with what, million, that means 10 to the power 6 to get it in terms of millions. That means how much actually how many parts is of that oxygens are present in millions, okay. So we can use these mathematical techniques, and if you use or you can if you solve this mathematics or this mathematical problems, then you can get the value as almost equal 5.8 gram per 10 to the power 6 gram. That means you will going to find out the value as 5.8 gram, okay, for 10 to the power, that means for or per million, understand, of seawater. So this is a very good example of representing the the amount of oxygen which are present in the seawater, okay. So again we can also use this technique to represent or to express the concentration of this fluoride and arsenic present in water, okay, drinking water. So actually we have already discussed this about that fluoride and arsenics, and also the importance, and also the the cause of some disease because of the presence of this fluoride and arsenic, okay. So this presence of fluoride and arsenic can also be expressed by this technique, because the fluoride amounts or the arsenic amounts are very little in that drinking water, okay. So actually a very little amount of that drinking water can so the presence of very little amount of that fluoride, almost 1.5, okay, can actually cause some disease, okay. So it is very harmful for us. So we have to remove the fluoride and arsenic from water, drinking water, before use, okay, understand. in your book, one more example is given here. You know, the pollutants which are present in the water or in air, that means atmosphere, okay, can also be expressed by using this ppm or sometime microgram per ml. Okay, so now let us discuss about the fifth way of expressions of that concentration, which is known as mole fractions. Okay, and this is very important, okay, for you. Mole fraction is actually represented by small x, okay, and some suffix are used which actually represents the components, okay. So the components may be solute, may be solvent, and actually the mathematically it can be represent or it can be defined as moles fraction of a component is equal to number of moles of components divided by total number of moles of components. Actually, what is the mole fraction? The fraction of that number of moles which are present inside that solutions. Okay, so that means how much fraction of that number of moles are mole of that components are present in the total number of moles of the solutions, which contains the solution solvents also. Okay, and let's suppose we are taking one binary solution. So binary solution means what? Binary solution means there will be two components. Let's suppose the components are A and B. Okay, and suppose in that solution number of component A or the number of moles of components A present is Na. Okay, and the number of component B present in that solution is let's suppose Nb. Okay, understood? So let's suppose we want to calculate the mole fraction of the component A. Okay, then what we have to do? We have to write the mole fraction of A, which is actually represented by Xa, is equal to number of moles of that A, which is Na, divided by total number of moles of components, that means Na plus Nb. Simple. Okay, so this is the equation for what? This is the equation for your binary solutions. So what about the other solutions which may have in a solution may have many solutes present inside that solution. Okay, and in case of that type of solution, let's suppose I number of components are present then, and let's suppose we want to calculate the mole fraction of that I number of ith component. Okay, ith component, mole fraction of that ith component will be what? Xi, which represent the mole fraction of ith component, is equal to, because we are trying to calculate what? Mole fraction of ith component, so we have to write here Ni. Okay, Ni divided by Ni plus, sorry, N1 plus N2 plus Nt plus to Ni. Okay, so here also it can be represented Ni divided by summation of Ni. So this summation means what? This summation means like add up. Okay, and there are some difference between summation and integration. I think we have already discussed about this. Okay, so integration means continuous additions. Okay, continuous, there will be no any gap. Okay, so there will be continuously increasing or continuously decreasing or continuous addition of something, so there will be no any add. Okay, gap. And in case of summation, actually we can actually sum up some numbers like 2 plus 3, that's are actually summations. But if you actually add continuously like 2 plus 2.0000001 plus 2.0000002 like that. Okay, so it is continuously increasing, there will be no any gap, visual gap. Okay, so it is integrations. Understand? So actually Xi is equal to Ni summation of Ni. So this is the mathematical expressions for the mole fraction of ith component. Okay, so actually here it is given in your book. It can be shown that in a given solution sum of all the mole fraction is unity. So it is very important. So always remember that the sum of all the mole fraction is equal to 1. So for binary solution it will be what? Xa plus Xb is equal to 1. For trinary solution, Xa plus Xb plus Xc is equal to 1. So that means the total so the addition of the mole fraction will be 1, because it is, you can actually prove this one also. Okay, and also the actually unit of these mole fractions are also very important. Actually by using the unit of the mole fraction, we can understand, we can have some idea about the physical properties of that particular solution. Okay, so actually in case of actually gaseous mixture also it is very important. It can be described the calculation involving the gas mixtures. Okay, so what type of gaseous mixtures is that. Okay, so we can understand by this unit of this mole fractions. Okay, let us try to understand the mole fraction by using the example 2.1. Okay, here we have to calculate the mole fraction of ethylene glycol in a solution if the ethylene glycol in that solution will be 20% by mass. Okay, so the given thing here is that they said that 20% of ethylene glycols are present in that solution by mass. By mass means what? That means we have to consider the amount of the solution as gram. Okay, gram, that means mass. Okay, and here it is said that it is in 20%, that means percentage. When something related percentage will be present, then what we have to consider? We have to consider the 100 as a the amount of the solution. Okay, and if it is in mass, then 100 gram. If it is in volume, then 100 ml. Okay, so here the mass of the solution will be your 100 gram. Okay, so here because 20% of the ethylene glycols will be present, then other 80 gram will be what? 80 gram will be your water. Okay, so we have now the value of or the mass of the ethylene glycols, which is 20 gram, and mass of water, which is your 80 gram in 100 gram of solution. Okay, but here what is our aim? Our aim is actually to calculate the mole fractions, and we know that to calculate the mole fractions of any components, we need to know about the actually the number of moles of that those components which are present inside that solution. So here the components are actually the ethylene glycols and the water. So we have the mass of the two components, which are 20 gram and 80 grams. Okay, so we need to convert this mass into number of moles. So how are we going to convert this into number of moles? We know that number of moles is actually equal to actually the mass of that substance divided by molar mass of that substance. Okay, so we have to find out the molar mass of the these components, which is actually ethylene glycols and the water. So molar mass of the ethylene glycol can be calculated like this. Actually, we know that the mass of the carbon is 12 and 2 carbon is present, so into 2 plus hydrogen mass is 1 into how many hydrogen is present? 6, so into 6 plus again oxygen 16 plus 2 is equal to 62 gram per mole. So that means molar mass of the ethylene glycol is 62 gram for 1 mole. Okay, so and similarly for water it will be your 18 gram for 1 mole. Okay, the molar mass. So number of moles of that ethylene glycol will be what? How many ethylene glycols are present? 20%, that means 20 gram in 100 gram of solution. Okay, so 20 gram divided by 62 gram is equal to this amount of moles. So 0.322 moles of that ethylene glycols will be present. So and number of moles of water will be what? 80 divided by 18. Okay, it is the mass of the water which is present inside that solution divided by molar mass of water is 18 gram per mole, so 4.444 mole. Simple. Okay, so the mole fraction of the the glycol, ethylene glycol, will be what? Is equal to moles of the ethylene glycol divided by moles of ethylene glycol plus moles of water, which is equal to 0.068. So similarly we can calculate the number actually mole fraction of water, which is 4.44 moles divided by the total amount of the number of moles. Okay, is equal to 0.932. Okay, so actually we can even calculate the mole fraction of water by actually subtracting the value of the mole fraction of that ethylene glycol from 1, because we know that the total mole fraction is always 1. Okay, so we can do this way also. Okay, so this is a very important. So please remember this point: total if you add the or if you sum up all the mole fractions which are present inside that the components, or sorry, in that solution, that means if you add up the all mole fractions of the all components, okay, and this value will be always 1. Okay, so this is all about the mole fractions. So I think you understand this, and this is very important. Okay, and one question often came from this this mole fractions this topic, mainly the numerical problems. Okay, so please remember or try to actually understand about this mole fractions. Okay, very simple. Okay, in the next class we will discuss about the molarity and molality. Okay, and also the normality. Okay, so because this normality, molarity and molality, mainly molarity and normality are used in your practical. Okay, so mainly we are preparing some molar solution or some normal solution in triations, also in in different types of practicals in physical chemistry, also in inorganic chemistry also. Okay, so we have to know about this. Also in organic chemistry also we have to prepare some normal solution or molar solution in case of some synthesis. Okay, so we're going to discuss in details about these three types of the way of expressing the concentrations. Okay, so for today I think it is enough. Okay, so thank you.